Now let's take a look at this example, this figure. Okay, this figure explains the quicksort one more time. Okay, in the first partitioning, so we pick one pivot, okay, and then we arrange all the other elements so that the smaller elements will be on the left side of this pivot and the other elements will be on the right side. Okay, that's the first partitioning. So after this first partitioning, the elements are in a sense a little bit somehow sorted. Okay, so on the left side we have a small element and we have pivot, and then we have a larger one on the right side. Okay, so after the first partitioning, and then in the second partitioning, we focus on the left side first and then we focus on the right side. So when we focus on the left side, okay, and then we pick a pivot and we rearrange all the elements in the left side. Okay, and then likewise we do the same thing with the right side. So pick a pivot and arrange all the elements. Okay, so let's say we have a pivot here, and then the smaller one in this side. Okay, all the small elements will be on the left side and the other one will be on the right side. Okay, and then next, okay, so then we apply the same thing to this side, and then this side, and then this side, and this side. So we apply the quicksort, we apply the partitioning 4 times. Okay, and then we keep doing this until we have one element in the side. Then everything is sorted. That's it. Now let's talk about complexity. Okay, so we have 2 different cases basically. So first one is worst case and the second is best case, and at the end of this slide we'll talk about average case. So first, worst case. So to us, to human, the worst case seems like the elements are random. Okay, so the order is random, or maybe descending order might be the worst case. Okay, but quicksort has different idea about the worst case. To quicksort, already sorted list is the terrible situations. This is quite interesting, right? So the input list is already sorted. Quicksort hates that kind of situation. That's the worst case. Why is that? Okay, let's think about this list. And in this list, okay, in this list, when we pick the one pivot with the first element, okay, and then after the first partitioning, what happens? The first pivot is still here, and this is the right side, and we don't have left side because this one is smaller than all the other elements. Okay, this is the first step. Okay, so what happens? With one step, we reduced the problem from n to n-1. Okay, that's it. And then we have to apply quicksort with n-1 element. Okay, that's the terrible situations. And again, with these n-1 elements, when we pick one pivot here, then after partitioning, then we have n-2 on the right side. So every time we just reduce the problem by 1. Okay, so from here to here. So basically, in the complexity, we have n times here, and then every time we have to check all the elements to partition, right? So we have n square problem here. See, that's the worst case. You have to count how many partitioning do we need. Okay, so in this case, we need n times partitionings. Okay, so every time we need n iterations, so that's why we have n squared. Okay, then let's talk about the best case. And best case is just random. So the numbers are randomly distributed, okay? Not just random. And at each step, list is evenly divided. It means, okay, in this list, when we pick one number as a pivot number, then this one is the middle element. Okay, so after partitioning, then this one will be here, and then we have n over 2 elements on the left side and n over 2 elements on the right side. So after partitioning, the left side and the right side, they have the same number of elements. Okay, that's the best case. So for every partitioning, we need n time complexity, because we have two indexes here, so we have to check all the elements. So every partitioning needs n time complexity. Okay, good. And let's say C is a constant for overhead. Okay, then let's calculate the time complexity of this quicksort for the best case. So that is T of n with n elements. Okay, and then after one partitioning, then we need some overhead, C times n. Okay, sorry, it's not overhead. That's the time complexity that we need to arrange all the elements. Okay, so basically we need two indexes for this direction and for these directions. So basically we have to check n-1 elements actually. So with some overhead, we have C times n here. And then after the partitioning, okay, if it is evenly divided for the best case, then we have n over 2 elements on the left side and n over 2 elements on the right side. So we have to think about this one. So we apply the quicksort algorithm to this n over 2 elements. Okay, so and then we have two cases. So we have 2 times T over n over 2. Okay, so after the first partitioning, so now we have these equations. Okay, good. And we can actually recursively apply this kind of trick. So we have a Cn here, and the 2 goes here, and then T of n over 2 can be rewritten by this. Okay, so we can rewrite that equation, and then if we keep doing this, and then finally we can get this one. And if we look at this one, Cn, and we can if we focus on these terms, then 2 and 2 cancel each other, and then we have a Cn. So we have 2 Cn here. So every time, whenever we go down to the next line, then we increase these equations. Then the question is, how many lines do we need? So every time n goes to n over 2, and n over 2 goes to n over 4, etc. So basically we have log n times iterations we need here. Okay, so instead of 2, we have log n here, Cn times log n. Okay, and then finally we have one element, and think about this one. In this case, we have a 2 part, but if we have many pivots, then basically we have n times T of 1. So when we have one element here, then we need T of 1, and T of 1, T of 1, T of 1. So we have n elements here. So basically we have n times T of 1. Okay, good. And T of 1 is actually constant because we don't have to do anything because it is already sorted. Okay, so this one is kind of linear, and this one is n log n. So in a big O notation, it is just n log n. Okay, good. So for the best case, where the list can be evenly divided, then n log n is the time complexity. Okay, and on average, actually we have n log n. So on average, usually maybe we when we divide after the partitioning, maybe pivot is around here, okay, or sometimes we have pivot around here, but on average, maybe we might have to multiply some constant, or we have to add some overhead, but on average it is n log n. Now you have some ideas about sorting algorithms, okay, and then before talking about any other sorting algorithms, let's talk about optimal sorting time. Okay, so in theory, what is the kind of the minimum time we need? Even if you are super genius, then what is the kind of minimum time complexity then you can achieve? Okay, so we'll talk about that. Yeah, in this slide, we want to talk about optimal sorting time. Okay, so let's go back to the quicksort algorithms. So we had a quicksort algorithm, and we talked about the worst case and best case and average case. Okay, given an algorithm, then there are many different cases. Okay, so given an algorithm, let's focus on the worst case. Okay, so if the algorithm is really great, okay, then in the worst case, still it needs n log n. Okay, so even the best algorithm needs n log n time complexity for the worst case. Okay, and the worst case depends on the algorithm. So for quicksort algorithm, the worst case is already sorted list. Okay, for insertion sorting algorithm, the worst case is not the sorted one. Worst one is kind of descending, maybe. Okay, so it depends on the sorting algorithms. Okay, so we are gonna prove how come we get this number. So why we need n log n even for the best sorting algorithms. Okay, so to sort a list, the sorting algorithms should decide the order by comparing elements. That's what sorting algorithm does, right? So we have to compare elements, and then we have to find a perfect order. Okay, and then in all possible permutations, every element should be compared with others at least once. All possible permutation means, the sorting is finding one permutation. Okay, given a list, then we want to make one permutation. So permutation, about the permutations, if you're familiar with the matrix, then you can think of a permutation matrix. So let's say we have 3 numbers, like 2, 3, 1, okay? Then we want to sort this list, then the output should be something like this, right? Then let's make a vector with 2, 3, 1, 2, 3, 1. And what kind of matrix do we need to get 1, 2, 3? That's easy. 0, 0, 1 and 1, 0, 0 and 0, 1, 0. So if we multiply this matrix to this vector, then we get 1, 2, 3. So see, 0, 0, 1 will get 1, and 1, 0, 0 will get 2, and 0, 1, 0 will get 3. So this one is a permutation matrix. Okay. So if we define a permutation matrix, then we can have a different order of the vector, different order of the elements. Okay, so we can come up with so many different permutations. So something like this. Instead of this matrix, then what about 0, 0, 1 and 0, 1, 0 and 1, 0, 0? If we use this one, then 2, 3, 1 will be 1, 3, 2. Okay, so we can come up with so many different permutations. Actually, in this case, we can come up with the 6 permutation matrices. Okay, and in all possible permutations, every element should be compared with others at least once. So this might be a little confusing, so don't worry. In the next slide, we'll talk about it with a good example. Okay, so we have three elements. In this case, instead of 1, 2, 3, we have a K0, K1, and K2. Okay, and we don't know. Maybe let's say, oh, this one is 2, 3, 1, or it could be 3, 2, 2, 1, or 1, 2, 3. We don't know. Okay, so we have three elements. Okay, and then with three elements, how many kind of orders can we get? Actually, there are 6. Okay, so 1, 2, 3, 4, 5, 6. So we can make 6 permutations. Okay, so no more than this. Okay, to get these permutations, we can use this binary tree. Okay, first we compare K0 and K1. Okay, so depending on this result, if K0 is smaller than K1, and then we can compare K1 and K2, and if K1 is smaller than K2, then we can stop. Just the 2 comparison is enough to get this sorting. Okay, or if K2 is smaller than K1, then we don't know, we are not sure that K2 is greater than K0 because we never compared. K0 is smaller than K1 and K2 is smaller than K1, then we have to compare K0 and K2. So depending on the result, then it could be this or this. Okay, so likewise, if K1 is smaller than K0, okay, then we follow this direction. And then if K0 is smaller than K2, then we stop. We know the order. Otherwise, we have to compare K1 and K2. Okay, so by this tree, we have 6 permutations. 1, 2, 3, 4, 5, 6. So we can generate 6 permutations with this tree. And in this tree, we compare K0 and K1, and K1 and K2. Okay, and then K0, K2. So we compare these elements, and sometimes in this tree, sometimes we compare K1 and K2 here and here. Okay, and sometimes we compare K0 and K2 here and here. Okay, that's what the previous slide said. Okay, now in the previous tree, the number of leaf nodes is the number of possible permutation n factorial. So let's go back. So we have 6 permutations. 6 is coming from 3 factorial. 3 factorial is 3 times 2 times 1. Okay. Why is that? Think about these combinations. So we have 3 elements. Then first, we have to choose which one should be the first element. So out of 3, we have to choose 1. So we have 3 cases. And once we pick the first element, then now we have 2 elements. Then out of 2, we have to pick 1. Okay, and then there's no other options. That's why we have 3 factorial to get the permutations, all the permutations. Okay, so now the leaf node is the number of leaf node is the number of possible permutation, which is n factorial. Okay, and the level of the leaf node is the number of comparisons required to know the order of elements. So the number of comparisons to get this permutation is the number of comparison is actually the height of this tree. Okay, and actually tree height is the number of comparison in the worst case, right? So in these examples, this is the worst case, this one or this one or this one or this one. So we have 4 different worst cases. Okay, and the tree structure is determined by sorting algorithms. Okay, so why do we compare K0 and K1? Why? That's our algorithm. So we compare K0 and K1 first, and then we compare K1 and K2, and then K0 and K2. Okay, so if we have a different sorting algorithm, then it will start comparing other elements. Okay, so yeah, tree structure is determined by sorting algorithms. The optimal sorting complexity is about the minimum tree height containing n factorial leaf nodes. So the tree height is determined by the worst case, and we want the minimum tree height for the worst case. That's all about the optimal sorting complexity. Okay. This slide, we're going to prove that the optimal sorting time is at least n log n. Okay. So to understand this slide, you might have to refresh your memory about chapter 5. In chapter 5, we talked about the maximum number of nodes. So we will use that in this slide. Okay, so let's go through this slide line by line first. Okay, first, decision tree means the tree we have seen a moment ago. Decision tree to sort n elements has a height of at least log n factorial plus 1. So we're going to prove this with these lines. Okay, so first, n factorial possible list that can be made from n elements. That's what we said, right? So when we have n elements, then n factorial permutation is possible. Okay, and then a tree with height k has at most 2 to the power k minus 1 leaves. Okay, we already proved that in chapter 5. So if you're confused, then you have to go back to chapter 5. Okay, so now let's use some equation to express these terms. So 2 to the power k minus 1 should be larger than or equal to n factorial. Basically, in a binary tree. Okay, so at this layer, okay, we can have at most 2 to the power k minus 1 nodes. And in the previous slide, so in this tree, we have some permutations at this layer and some permutation at this layer. Okay, so we have all the permutations in the different layers. So at least this layer, the last layer, should be larger than or equal to n factorial. Then probably maybe we might have some permutation somewhere in the middle of these trees. But this layer, the maximum number of the nodes, the leaf nodes of this layer is 2 to the power k minus 1. That should be larger than n factorial. Then if we take a log, then we can get this one. So k is the height of the tree, and the height is larger than these equations. It means we need this many comparisons to get to the worst case permutations. Okay, and second, okay, let's talk about the complexity of sorting problems. Okay, the number of possible lists is n factorial, and n factorial can be rewritten by this. Okay, this is just the definition of factorial. Okay, and then let's truncate this part. Okay, so multiplication of 1, 2, 3, 4, 5 up to n over 2 minus 1. Then obviously this is larger than this one. Okay, so we just truncated some numbers. Okay, and then we can replace this one with n over 2 and the n minus 1 with n over 2, n minus 2 with n over 2. Then yes, this one is larger than this one, and this one is actually n over 2 to the power of n over 2. Okay, then if we take a log here and the log here, then it will be n log n over 2. Okay, so we get that. So look at this one. We have a log n factorial here, and the log n factorial is larger than this. And in the bigger notations, we ignore these constants. So this one is lower bound. Okay, so n log n is the lower bound of this log n factorial, and this one is actually lower bound of k, and the k is the height of this tree, which means k is the number of comparisons for the worst case. So we need that many comparisons. So the lower bound of the number of comparison is n log n. That's why best sorting algorithm needs n log n at least for the worst case.